Yo, so my animations are never this good, but bear with me. Today I wanted us to tackle a very common problem in so many mathematics competitions, including the IYMC, which I myself has attended. We start by considering an infinite plane with n lines, and no 3 are concurrent and no 2 are parallel. We need to find out how many regions exist in such a plane. Knowing that the plane is infinite, the lines must be infinitely long as well. The word concurrent means that no 3 lines ever intersect at the same point. So if there's an intersection, it's only formed by 2 lines maximum. I can explain the word parallel using a pair of lines. If the pair of lines were parallel, then considering that they're infinitely long in an infinite plane, these particular lines never meet. So on the plane we're given, every pair of lines must have an intersection point. We now understand every detail in this question. So let's start solving a problem that stumped many kids. I'll start by simply talking about problem-solving technique. We start by determining under what category of mathematics such a problem would fall under. It's obviously geometry, but with a little combinatorics, so combinatorial geometry. Though the combinatorics we're talking about here is the number of ways a specific number of lines can intersect themselves. The approach to such a problem usually involves maybe playing around with a number of lines to find some clue. But we won't be focusing on the lines and regions since the two are of different dimension. Let's try finding some relationship between the number of lines and the intersections instead. Our first case is the one line, where there are literally 0 intersections. Oh, and by the way, each time you see the texts over here, they're simply denoting a mystery function that's mapping a specific number of lines, n, to the corresponding number of intersections, u. We add another line that's not parallel, so this guarantees an intersection. And now we add a third line. Due to the concurrency statement, the third line mustn't go through the same intersection, and it mustn't be parallel to any of the other 2 lines, thus forming 2 new intersections with the 2 previous lines. We can take it to 4 lines. Using the same logic, this forms 3 new intersections with the 3 previous lines. Generally speaking, when we add an nth line, it forms 1 intersection with each of the previous n-1 lines. So each new line adds n-1 intersections. And this can be seen since the function of 1 equals 0 and the function of 2 equals 1. The function of 2 is basically the second line, and it therefore adds 2 minus 1 intersections. And the function of 3 would add 3 minus 1 intersections. Let's now use this function equation to find a standard formula for this mystery function. Let's first erase everything, maintaining the function of 1, which will need to generate the other functions. Now that we have the function of 1 and the function equation, let's find out the other function values. We can start by taking 2 through the equation. This gives function of 2 equals the function of 1 plus 2 minus 1, which shows that the function of 2 equals 1. Now that we have the new function value, let's find the function of 3, which is given by a function of 2 plus 3 minus 1. This turns out to be 3. We can also find function of 4, which is the function of 3 plus 4 minus 1, which is 6. Let's go straight to the function of 5. This is the function of 4 plus 5 minus 1, or the function of 4 plus 4, which is 6 plus 4, that's 10. Now, it's a little predictable what the function of 6 could be. Well, 15, right? Because triangular numbers, blah blah blah, but how are we sure this is true? Well, we could look deep into the function of 5, which is the function of 4 plus 4. When we dive deeper into the function of 4, we find function of 3 plus 3. And into the function of 3 is function of 2 plus 2, and into the function of 2 is function of 1 plus 1. And the function of 1 is 0, so this can just be 1. Let's ignore this bracket since addition is commutative. This is the triangular number sum, which means that the function values are triangular numbers. So one formula could be n into n plus 1 over 2. Or is it? Because the triangular numbers only start at the function of 2, since the function of 1 equals 0, which is not a triangular number. So after noticing that these triangular numbers lag out by 1, a new formula could be got by plugging in the n-1th value for n. This gives n into n-1 over 2. So now we have a standard relationship between the number of lines and the intersections. Now, how do we get from intersections to regions? Well, again, it's not straightforward. Though, what we could do is move from intersections into line segments, then into regions. This doesn't seem helpful, but you see in a few. To understand how intersections relate to the line segments, we can consider multiple lines in a plane. Here we consider 4. Then we add a 5th line, which will be intersected 4 times by the previous 4 lines. If there are x intersections, then there are always x plus 1 segments. So this new line has 5 segments. Another not so obvious thing is that each new segment adds one more region. An interesting way to visualize this is by ignoring the line we've just added. Then we highlight the regions the line previously crossed. Now reconsider the line, and you find out that it divides each of these regions into 2. So we can call the regions on the left the new regions, which when you observe have been formed per segment. This justifies the statement. So since we've added 6 new segments, then we've added 6 new regions. This is like a very good relation, because we can consider when we add one line segment, which is a 1 line 0 intersection case. Then we only add one new region. With a second line, we add 2 new segments, since we form one new intersection. So we add 2 new regions. We already know what's gonna happen with the third line. Since we'll be adding 2 new intersections, then we add 3 new segments, thus 3 new regions. And you notice the fact that we keep adding whole number regions, and the whole numbers are consecutive? Then we have a triangular number sum. And this works straight from the first segment. And the first segment is one line, or n, so the formula could be n into n plus 1 over 2. But we've only considered adding new regions and not the very first region when there are no line segments. So n into n plus 1 over 2 plus 1 as the very final solution for this mathematical problem. Now this may get you thinking, why did we calculate the formula for the intersection? Now this was not related to the solution, but this is an exploration video where I usually want to engage my audience and for better understanding of various concepts. Anyway, with that having been said, the origin of this problem is rather messed up. It is so-called a problem that stems up from many mathematical studies. The mathematicians want to find a special way of cutting a pizza maximizing the regions, regardless of the size, of each one, which brings about the various restrictions, such as no 2 cuts are parallel and no 3 are concurrent, which maximizes the number of regions regardless of their size, of course. But the problem seen here is an infinite plane, since there could be lines that are not parallel, but the difference in angle could be like 0.0001, and that's why we consider an infinite plane, because with a finite one, you may not have enough space to see these lines meet, yet they're actually not parallel. And this leads to actually counting less regions. And today the problem is known as the lazy Carteret's problem. Anyway, if this delights you as a math lover, and if you think the video is legit, which I of course think, I recommend you liking the video. This took me days to animate, oh my god. And obviously, subscribe!